You know the feeling. The countdown on the screen hits 0. You slam your mouse on that buy button for tickets to see your absolute favorite artist. And you know a million other people are doing the exact same thing. Your heart is pounding. It feels like a lottery, right? Just this crazy digital scramble. But have you ever actually stopped to wonder what is happening behind that one single click?
Okay, let's really get into this, because what looks like the simplest thing you can do on a website, just clicking a button, is actually hiding one of the most intense, high-stakes challenges in all of system design. We are going to pull back the curtain and look at the incredible engineering that makes sure your ticket is your ticket and nobody else's. So from our side of the screen, it's this easy three-step dance. You see the event, you pick your seat, and you pay. Simple. But for the engineers who build this stuff, it's a war against three absolute giants. First, consistency, which means one ticket can never ever be sold twice. Then scalability, so the system can handle that insane rush of fans all at once. And finally, concurrency, which is all about managing millions of people trying to grab the exact same seats at the exact same time. It's a massive digital balancing act.
Let's start our journey right at the moment you click on that perfect seat. Now, the system can't just sell it to you instantly. I mean, you need time to find your credit card and type everything in. So it kicks off this sort of digital handshake, a temporary hold that basically says, all right, this seat is yours for now. This whole process is actually broken down into two really clear phases. First, when you pick a seat, the system puts a temporary 10-minute lock on it. This is the reserve step, and it takes that seat off the market so no one else can even see it. It's only after that seat is safely reserved for you that you move on to phase 2, confirming your payment to officially make it yours.
Right, and this is a huge problem. Think about it. If that seat is just marked as reserved somewhere, and then your Wi-Fi dies or you just close the tab, well, that seat could get stuck in limbo forever. It would never go back on sale. The venue would slowly lose all its best seats. So how do they fix this?
The solution is just so elegant. Instead of a permanent reserved flag, the system uses something called a time to live, or TTL. You can think of it like a self-destruct timer on your reservation. If you don't finish buying that ticket within the 10-minute window, the lock doesn't need to be manually removed. It just evaporates. And just like that, the seat is automatically and safely returned to the pool for the next fan in line. Brilliant.
Okay, so that handles one person. But now let's get to the main event. What about the digital stampede? That moment, a superstar's tour goes on sale and millions of people all hit the site at the exact same second. This is where the real chaos begins. Just try to picture it. Over 1 million fans all hammering the system, all fighting for just 50,000 seats. They're not just browsing, they are all trying to perform an action, a booking, at the exact same microsecond. This isn't just a lot of traffic, it is a full-blown concurrency nightmare. So here's the bottom line. In the middle of all that chaos, there is one sacred, unbreakable rule. A single seat cannot be sold to two different people, period. This is that core principle of consistency. You just can't have two fans showing up to the concert with a valid ticket for seat 17B. One of them has to win the race, and the system has to guarantee that result 100% of the time. Now, to solve a problem this massive, engineers didn't just come up with one perfect answer on day one. It was an evolution of ideas, really a journey through different attempts to build a system that's both fair and can actually scale. So let's walk through how they got there. So, the first and most obvious idea is, hey, let's just treat it like a real-world ticket line. Every single request gets into one big, single-file queue and gets processed one by one. Simple, right? Wrong. With 1 million people, that line would get so long, so fast, that requests at the back would time out before they even got a chance. The entire system would just grind to a halt, a complete and catastrophic failure.
Okay, so one line is a disaster. What about multiple checkout lines? You know, like at the grocery store? We could have a bunch of different processors handling their own queues of requests. This is definitely faster, but it creates a brand new problem. Before any of those queues can actually book a seat, it has to check with a central source of truth, a distributed lock, to make sure another queue isn't booking that same seat. And just like that, we've created a new traffic jam, and everyone is stuck waiting at that central lock.
So, if the locks are the problem, is it possible to build a system that doesn't need them at all? The answer is yes, and the breakthrough is a concept called sharding, which lets you create intelligent queues that don't need to fight with each other. This is really where the design goes from clever to pure genius.
Sharding is all about smart routing. Instead of just random queues, you route requests based on a specific key.
So for instance, all requests for the Taylor Swift concert go to this processor, and all requests for the NBA Finals go to that processor. Or you can get even more specific. All requests for Section 101 of the Taylor Swift concert go to one worker, and all requests for Section 102 go to another. By doing this, any requests competing for the same group of seats are guaranteed to line up in the same single-file queue. No conflicts, no race conditions, and no need for locks. It's orderly, it's efficient, and it's massively scalable.
Now, this lockless booking engine is absolutely the star of the show, but it can't handle that digital stampede all by itself. It needs a supporting cast, a few other critical systems to manage the crowd and keep everything from collapsing under that first huge wave of traffic.
And two of these systems are absolutely key. First, the virtual waiting room. This is basically your digital bouncer. It holds that massive crowd of users outside and only lets a manageable number in at a time to actually use the booking system. This protects the core system from getting totally overwhelmed. And second, you have an optimized search engine. This lets millions of people browse and search for events without ever bothering the critical booking database, which means the whole site stays lightning fast for everyone.
So after all of that, let's just zoom out for a second and appreciate this invisible architecture that makes the whole experience possible. It really is a complex dance of different systems, all working together in perfect harmony.
From that first click on a seat, to that temporary TTL lock, to the intelligent sharding that sends your request to exactly the right place, and finally, to your confirmed ticket, a whole symphony of engineering works in milliseconds to make sure that out of 1 million people, you and only you got that specific seat. It's just an incredible feat of speed, fairness, and absolute consistency.
And all this leaves us with one last really interesting question. Some systems, like for high-demand train tickets, actually take away your ability to choose a specific seat. You just say, I need a ticket, and it gives you one. This makes the whole concurrency problem way, way simpler. So what do you value more? The total freedom to pick that perfect spot, row 5, center, or the simple guarantee that you'll just get in the door? It's a fundamental design trade-off that really shapes our entire digital world.